Hello, my name is Eugenio Rones Lozano, and the title of my talk is a Maple-based introductory visual guide to Gröbner bases. This is a joint work with Eugenio Rones Macías. We are both teachers at the Universidad Complutense de Madrid. In fact, he's my father and Ph.D. advisor. In 1975, he published a work entitled something that could be translated as geometric interpretation of ideal theory. That was an illustrated, explained detail of ideal theory. There are many books on ideals and algebraic varieties, but we think there's a lack of introductory ideas for Gröbner bases and the interpretation of algebraic systems. Many times the users of some mathematical software are not really involved in all the details of the theory in the background, but just use it and have a light idea of the background of the theory. So we'll try to explain what a Gröbner basis does and how it can be used for non-mathematicians. This is not a talk for algebraists or experts in computer algebra. We first begin by loading the plots package and the Gröbner basis package and defining a couple of functions that extract from a polynomial system, either given in explicit or implicit form, the polynomials of the system. As a first remark, if K is a commutative field, K of xy or K of xyz are commutative polynomial rings. We'll try to give as very little explanations and details of the mathematical background, but we need some words and some definitions. Here, K is the base field of the polynomial ring, and there's a problem that we can only draw in R2 or R3, and really, for many of these procedures, what is needed is that the base field is algebraically closed. That is, we should plot in C2, C3, but we can't do that. Well, linear equations and linear systems, also known as systems of simultaneous linear equations. A linear equation is an equation involving polynomials which variables occur linearly, that is, to the first power with no product of variables. And it can be of the form polynomial 1 equals to polynomial 2 or polynomial equal to 0. And the set of zeros of a linear equation, that is the set of points where the equation is satisfied or where the polynomial pole vanishes, is called the zero set or zero locus of the equation. It is a line in the 2D case, a plane in the 3D case, and an affine hyperplane. It is a generalization of the idea of plane of R2 in the general n-dimensional case. The zero set of zero locus of a linear system is a set of points where all the equations of the systems are satisfied. So it's an intersection of line planes or hyperplanes in the 2D, 3D, or n-dimensional cases. And well, a linear system can be changed obtaining a system that is equivalent. And that can be done if an equation is added to an equation, a linear combination of the other equations, that's an expression of the form numbers times the other equation, is added to an equation. There are well-known methods for solving linear systems, like Cramer's rule, Gaussian elimination, etc. But let's try to give the geometric idea of what is done. For instance, if we have the equations y equals to x plus 1, the zero set of that equation is as a line. Another example, 3 times y equals to 2 times x plus 1. And we have this polynomial, this equation is equivalent to this polynomial equal to 0. This is its plot. And for instance, if we give a condition like this, z equals to x plus 2 times y, in the 3D case, we have a plane. So if we consider linear systems, that is sets of linear equations, what we can get of zero sets is the empty set, points or lines in this 2D case, plus planes in the 3D case. The system can have a unique solution, can have a point as solution. For instance, if we consider this system, y equals to minus x plus 2, y equals to x, the zero locus is the intersection of the two lines. We can plot it in Maple either in explicit form or in implicit form. And if we compute the Gröbner basis of this set of polynomials, we obtain y minus 1, x minus 1. Well, here we ask Maple to consider an ordering for the monomials that is pure lexicographical. It's an ordering similar to the one used in dictionaries, and an order for variables, x, y. The order for variables can be changed, and also other ordering for monomials can be chosen, for instance, total degree, where the degrees in each variables are added. In this case, it doesn't matter which order we use, but that can change depending on the set of polynomials considered. What does the Gröbner basis do in this case? Well, the solution, the x equal to 1, y equals to 1, is described at the intersection of these two lines that are parallel to the coordinate axis. The system can be equivalent to another system with more equations. In this case, a third equation is considered that doesn't add any extra condition to the solutions, that has the same solutions. And what the Gröbner basis does, of course, is to give what an algebraist call another basis of the ideal generated by those polynomials, that is to describe it in a simpler way, the same way as before. And of course, if we add yet another more equation, as it describes the same thing, it's equivalent to the original system, the Gröbner basis is the same. It could happen that the system had no solution. One possibility in the two-dimensional linear case is that we have two parallel lines. In this case, there's no point line at the same time of both lines. So what we get as Gröbner basis of the polynomial linear system is 1. That is, the system is equivalent to the equation 0 equal to 1. That obviously has no solution. If we try to plot it, we obtain the empty set. Another possibility for a system in 2D that has no solution is, for instance, to have two parallel lines plus a line intersecting them. So there can be many cases where there are no solutions. There can be an infinite number of solutions when the two equations are really equivalent. So it is reduced to one of them. In this case, if we plot the Gröbner basis, we obtain exactly the same line. In the 3D case, we have more possibilities. The zero sets can be the empty set, a point, a line, or a plane. For instance, it can be a unique solution, a point. In this case, we have 3 planes, as illustrated here, and the only solution is the point that I'm marking. The Gröbner basis of this system is z plus 1, y, x plus 1. That is, another 3 planes. But if we plot them, let's say that it's somehow given in a simpler way. The 2 monomial orderings that we mentioned before, that is pure lexicographical and total degree, what try to do respectively is to have as few variables of one kind as possible, or degree of that variable, or to have a total degree as low as possible. So from an intuitive point of view, it's reasonable that it tried to give it in the simplest possible way. In this case, the 3 planes are parallel to the planes containing 2 coordinate axes. The zero locus of the system can also be a line. For instance, it can be the intersection of 2 planes. And again, what the Gröbner basis does is to provide a couple of planes simpler than those given. In this case, one of them is vertical. The other one can be vertical, as the intersection line is not parallel to any of the coordinate axes. It can happen that the locus, the zero locus, is directly a hyperplane. In this case, for instance, 2 equations describe the same hyperplane, and the Gröbner basis returns one hyperplane. We plotted, obviously, in the same one that was input. The zero locus of the linear system can also be the empty set. For instance, here we consider 3 planes. 2 of them are parallel, and a third one intersects them. Obviously, it's not possible to stay at the same time on the 2 parallel planes and on that third plane that intersects these 2 planes. The Gröbner basis, of course, is 1. It's equivalent to equation. System is equivalent to the equations 1 equals to 0, and so the implicit plot is empty. Another possibility are, for instance, 3 planes containing the lateral faces of a triangular prism. It's not possible to lie at the same time on these 3 planes. And again, the Gröbner basis is 1. It's the ideal generated by number 1. Okay, let's move now to the algebraic equation and algebraic systems case. An algebraic equation or polynomial equation is an equation involving polynomials. It can be of the form polynomial 1 equals polynomial 2 or polynomial equals to 0. And the set of zeros of an algebraic equations is satisfied in the first case, where the equation is satisfied, or where the polynomial pole vanishes. That set of zeros is also called the zero locus of the equation. It is a curve in the 2-dimensional case, a surface in the 3-dimensional case, and an affine hypersurface in the n-dimensional case. The zero set, zero locus of an algebraic system is the set of points where all the equations are satisfied. It is also called the affine algebraic variety of the ideal generated by these polynomials, but we'll try to avoid possible formalization. This zero set or zero locus or algebraic variety is the intersection of curves, surfaces or hypersurfaces in the two-dimensional, three-dimensional, n-dimensional cases. An algebraic system, an equation, can be substituted by what is called an algebraic linear combination of the other, can be substituted by the equation plus an algebraic linear combination of the other equations. An algebraic linear combination is similar to a linear combination, but instead of multiplying by numbers, you can multiply the equations by polynomials. There are methods for solving algebraic systems, like Gröbner basis. And here solve means expressing it as simply as possible, because the situation is not as simple as in the linear case. Well, then an algebraic equation is something like this: y equals to x to the fourth power minus 5 times x squared plus 4. And this is the zero locus of the equation. It can also be given in implicit form. Here, the x and the y's are mixed in one side of the equation, and you can obtain from there the expression of y in a polynomial form. And in this case, we have an ellipse as zero locus. In the three-dimensional case, we have, for instance, in explicit form, equations like this. Here z is expressed as a function of polynomial function of x and y, and this would be the locus. Well, something important is that in the algebraic case, when we consider algebraic equations, the zero set can have more than one irreducible component. This should not be misunderstood with the zero set of a system of two equations. Here we have just one equation, and let's say that somehow the plot has two parts, two independent parts, two irreducible components. In this case, this is a fourth degree polynomial, and this is the zero set of that single polynomial. Well, let's move to algebraic systems. First, we'll see some examples in the 2D case, and later in the 3D case. In the 2D case, the system can have a unique solution. In this case, we have the three polynomials. Two of them are parabola, and the other one is a straight line. The only real solution is 0.11. If we compute the Gröbner basis, sorry, 10, we compute the Gröbner basis, the polynomial set of polynomials returned is y, x minus 1. So the system which equation had these zero sets can be represented in a simpler way this way. Another example, if we have a hyperbola and a straight line, again we have a single solution, a point, and the Gröbner basis is formed by these two polynomials in this case, and what we have here is the intersection of two straight lines. Well, from a more technical point of view, really, this is y minus 1 squared. Algebraists would say that this is a primary ideal generated by this polynomial, and the variety is the same as that of its radical. But, well, thinking from a naive point of view, we have described this point this way, this intersection of these lines. The only thing is that this line is described not directly. Sometimes the solution can have more than one component. In this case, we are intersecting this parabola with this couple of lines. So this is, we are not asking, it's not a system of three equations. We are not asking to be at the same time in the two lines and the parabola, but to be at the same time in the parabola and in the couple of lines, the two red vertical lines are the locus of this equation, as can be seen here when we factor this x squared minus 5 over 2 x plus 3 over 2. The intersection is a couple of points, and the Gröbner basis is again a couple of polynomials, as we can see here, and the 2 points are described as the intersection of a line and a couple of lines. We can have cases with more than 2 components. For instance, here we intersect a cubic with a straight line, and the Gröbner basis is again a cubic and a straight line, but it's simpler because really this third degree polynomial consists really of these straight lines. So it has simplified the description of the system. The polynomial system can have a zero set that has more than one component, but not of the same kind. For instance, here, well, I don't know if it can be seen clearly, but one of the zero locus is in green. It consists of 2 vertical lines, and the other consists of a parabola and a vertical line. That's why this vertical line appears more or less in green, because it is at the same time yellow and blue. We can see here that the polynomials factorize, and they have a common factor. This is the vertical line x equal to 1. Here we have the 2 equations plot separately, and if we ask for the Gröbner basis, we obtain 2 polynomials, and the plot is the intersection of these lines. Again, we can see that they have a common component, that is this vertical line. So one is the 2 vertical lines, and the other is the 2 perpendicular lines. So again, it has simplified the description. Of course, the zero locus of an algebraic system can be the empty set. In this case, it's impossible to satisfy at the same time to be on the blue and the red parabolas. So the Gröbner basis obtained is 1. But we must be very careful here, because sometimes there can be missing components. For instance, if we intersect these 2 cubics, there's only one point as intersection. But if we obtain the Gröbner basis, we have a simpler description as above, intersection of 2 lines. But when we solve here the systems with common solve, there are also complex values. So there are 2 other intersection points between the 2 cubics. Also, we must be careful because the intersection in R2 can be empty while not in C2. For instance, these two circumferences have nothing in common in the reals. But if we compute the Gröbner basis, it's not one. So there are solutions. Let's try to plot it. It has two components, but when we plot it, we obtain only one. So what is happening is that the other component, the one that should have been plotted in cyan color, is empty. If we solve it, we can see that x equal to 0 is what has been plotted in pink, but there's here another locus that is imaginary. Well, different systems can lead to the same Gröbner basis. For instance, if we consider the intersection of this circle, this cubic, and this parabola, we obtain as description a couple of vertical lines intersecting a horizontal line, because there are two intersection points. But that can be described in other ways. For instance, at the intersection of these two parabolae. And again, the 3D case is a bit more complex. We have cases when there's a unique solution. For instance, here we intersect these two elliptic paraboloids and two planes, and there's a single intersection point here. The Gröbner basis returns three planes parallel to the planes containing two coordinate axes, and the description is as simple as these three planes because it's describing this point. Sometimes it's not so straightforward. For instance, if we only consider the three elliptic paraboloids of the previous example, and we obtain this as a solution, this is in fact the Gröbner basis, a simpler description of the system. But if we plot, we only obtain a plane. What has happened is that here there's only one real solution. That's x and y equal to 0. But there's a whole locus in the complex case. So it should have plotted a point here. Normally, the situation can be that the system, the intersection of two surfaces is a curve. Let's say that it's like saying that the intersection of two planes is normally a line. Here, for instance, we have an intersection of two quadrics. The intersection is a curve here. And if we compute the Gröbner basis, we obtain a plane, a vertical plane, plus a cylinder, a parabolic cylinder. In this case, there's something strange with Maple, that is that it doesn't plot the y-square, and we have to introduce the corresponding prime ideal to y-square, that's why. And then the description of the intersection can be given this way. Again, there can be more than one component. For instance, in this case, we're intersecting sphere, vertical plane, and an elliptic paraboloid. We have one intersection point here and one intersection point in the background. The Gröbner basis in this case returns this solution. So we have here a couple of planes, a vertical plane and a cylinder, parabolic section. We have the intersection point here and here. There can be cases with no solution. For instance, if we intersect this cylinder, which vertical cylinder, which section is a cubic, with this plane and this plane, it's impossible to satisfy the three conditions at the same time. So the Gröbner basis is 1. And there can be cases where there's no solution, but no real solutions, but complex solutions. For instance, the intersection of this sphere and this paraboloid, elliptic paraboloid, is clearly the empty set in the reals, but the Gröbner basis is not 1. That's because if we try to solve, this is how it describes the intersection. Instead, the sphere is substituted by a vertical plane, and it's because the solutions are all imaginary. Here, minus 12 is bigger than 6 times square root of 3, so not possible to obtain if we subtract something else to obtain a positive value. Well, it's curious that the idea of what a Gröbner basis returns doesn't correspond to the idea of basis of a vectorial space. In a vectorial space, all bases have the same number of elements. That's the dimension of the vectorial space. Here, the number of elements of the Gröbner basis is not constant. Depending on the order considered, we can have different number of elements generating the ideal. So it's more related to a special case of set of generators of vector space, not of the ideal of basis of a vector space. They are generators of a very special kind, that they completely identify the ideal. Well, in this strange case, we have two generators. If we consider pure lexicographical order with z preceding y preceding x, we have this description. So the Gröbner basis has 3 polynomials, even if the input had 2 polynomials. If we change the ordering, we obtain 3 different polynomials, from 4 different polynomials. And if we use total degree with x preceding y preceding z, then we obtain the input polynomials. The importance of the Gröbner basis is that once the monomial ordering and the order for the variables are fixed, the Gröbner basis is unique for the polynomials of any equivalent system, that is for any ideal. So we can decide if 2 ideals are the same. Let's say if 2 systems are equivalent, just checking if the Gröbner bases are the same. For instance, if we give the circumference intersection of this paraboloid and this plane in this way, or in this way as intersection of a plane and a cone, this is a beta image, or in this way as the intersection of a sphere and 2 elliptic paraboloids, in all cases, the Gröbner basis is the same if we use the same ordering for monomials and the same ordering for the variables. And this is the description of that circumference. We have here different ways of describing that circumference, and somehow the Gröbner basis is simpler. It's simpler to describe that circumference as a cylinder of and in its intersection with a perpendicular plane to its axis. Applications of Gröbner basis. There are applications in many fields. For instance, an immediate one is to check if a curve is contained in a surface. It's enough to add the equation of the surface to the equations of the curve. If the Gröbner basis is the same, the curve is contained in the surface. For instance, a very curious example is to check if a graph is tricolorable. This is an example by Trager. And there are other examples like automatic theorem proving geometry, knowledge extractions in rule-based expert system, etc. This talk was intended, as you see, for non-mathematicians and try to illustrate the difficulties of interpreting what the Gröbner basis does, and at the same time to understand what it does with as little theory as possible. Thank you very much.